The Big Bang is a lie, not the science, the name. A man who despised the theory coined those three words on a BBC broadcast to ridicule the idea. His ridicule became the brand, and the brand hides a deeper problem. What everyone calls the Big Bang does not describe the beginning of the universe, not even close. The actual beginning is a wall that no equation can see through. But the wall is not the end. On this side of the wall, something remarkable happened. The universe left behind evidence, not of the beginning, but of what happened in the seconds and centuries after. A faint glow, ancient and everywhere, the leftover heat from a moment when light itself was trapped. A recipe for the first elements, forged in the opening 20 minutes, accurate across 9 orders of magnitude. Except for one ingredient. One number is wrong by a factor of 3. Nobody knows why. A name born from contempt. Proof that arrived by accident, from engineers who had no idea what they had found. A recipe with a crack nobody can close. The universe left behind a trail, leading back toward a moment no instrument can reach. And one question nobody expected, whether that trail will survive long enough for anyone to follow. If you enjoy journeys that change how you see reality, hit that like button and subscribe. Everyone knows the name, Big Bang, the most famous phrase in the history of science, the one that supposedly explains where everything came from. Except the name does not explain anything at all. The name is a joke, a piece of mockery. And the man who invented those 3 words wanted the idea behind the words to die. 1949, the British Broadcasting Corporation aired a radio program called The Nature of Things, and the host was a physicist named Fred Hoyle. Hoyle was brilliant. Nobody in the astronomical community questioned that assessment. Hoyle had already solved one of the deepest puzzles in nuclear physics, a problem called the carbon bottleneck. The puzzle was simple to state and maddening to solve. Stars fuse hydrogen into helium easily enough, and helium into beryllium. But beryllium-8 is unstable. The nucleus falls apart in a fraction of a trillionth of a second. Without a way past beryllium, stars could never build carbon. And without carbon, the periodic table from element 6 onward had no origin. No carbon, no oxygen, not a single amino acid. No pathway to life. Hoyle predicted a way through. Hoyle argued that the carbon-12 nucleus must contain a previously unknown energy state, a resonance at a precise energy level that would allow 3 helium nuclei to combine before the beryllium intermediate disintegrated. The prediction was specific enough to test. Lab teams found the resonance exactly where Hoyle said the resonance would be. The discovery meant stars could forge carbon, and from carbon, everything heavier. Hoyle was the reason astrophysicists understood how stars manufacture the raw material of planets, of oceans, of bones. The achievement alone would have cemented a legacy in any era of physics. But Hoyle had a problem with the universe. The expanding universe hypothesis, championed by a Belgian priest and physicist named Georges Lemaitre, proposed that space itself was stretching and that every galaxy was rushing away from every other galaxy. The implication was inescapable. If the cosmos was expanding now, then tracing the expansion backward in time led to a moment when all matter, all energy, all of space was compressed into a single point of unimaginable density. A beginning. Hoyle found the idea repulsive, not because the mathematics was flawed, but because the implication felt religious. A single moment of creation sounded like Genesis dressed in equations, and Hoyle wanted no part of the story. Hoyle was not alone in the discomfort. Albert Einstein himself had struggled with the expanding universe years earlier. When Einstein first applied general relativity to the cosmos in 1917, the equations told Einstein the universe could not be static. The fabric of space should be expanding or contracting. Einstein found the result disturbing. The prevailing wisdom, centuries of philosophical tradition, said the universe was eternal and unchanging. So Einstein added a term to the equations, a cosmological constant, a mathematical patch designed to hold the universe still. The patch worked on paper. The universe balanced. Then Hubble published the expansion data, and the universe was not still. Einstein reportedly called the cosmological constant a blunder, the biggest blunder of a career. In the end, the greatest physicist in history had not trusted the equations. Those equations had been right. Einstein had been wrong. Decades later, the accelerating expansion would reveal that a cosmological constant is actually needed, but for entirely different reasons than Einstein imagined. Einstein was right to add the number, wrong about the purpose, and wrong to remove the constant. The universe, as always, had a sense of irony that no physicist had requested. Hoyle championed a rival model called the steady-state universe. In the steady-state picture, the universe had no beginning and no end. Space expanded, yes, but new matter continuously appeared in the gaps, filling the voids left behind by the retreating galaxies. In the steady-state cosmos, every direction looked the same, at every moment, for all eternity. Beautiful. A universe without a birthday. A cosmos that simply was, and always had been, and always would be. Testable. And championed by brilliant people. Hoyle, along with Hermann Bondi and Thomas Gold, published the framework in 1948, 1 year before the broadcast, that would change scientific vocabulary forever. So on that 1949 BBC broadcast, Hoyle dismissed the rival hypothesis with a phrase designed to make the idea sound absurd. Hoyle called the concept a Big Bang. The phrase dripped with contempt. The intention was ridicule. The delivery was casual, almost throwaway, the verbal equivalent of an eye roll. Hoyle wanted the audience to hear those words and laugh. A Big Bang. How silly, how unscientific. What a convenient idea for people who needed a creation myth, with a lab coat draped over the shoulders. The ridicule failed spectacularly. Hoyle had handed the opposition the most memorable brand in the history of science. The name stuck. Within a decade, the phrase Big Bang appeared in textbooks, in newspaper headlines, in the vocabulary of every educated person on the planet. And the man who most wanted the theory to fail had given the theory the most recognizable brand in all of science. Almost nobody who uses the phrase today knows the phrase was born from contempt. To most ears, the name sounds triumphant, definitive, like a celebration of the moment everything began. But the origin of those three words is the exact opposite, born from a sneer. Hold that thought for a moment, because the name is not the only thing wrong with the story everyone believes. The story has a deeper crack, and the crack sat in plain sight for more than 2 decades. Before the name existed, before Hoyle ever spoke those words on the radio, the expanding universe had a champion, a number, a measurement, and the measurement was catastrophically wrong. In 1929, an astronomer named Edwin Hubble published a paper, one that would reshape the human understanding of the cosmos. Working at the Mount Wilson Observatory in the San Gabriel Mountains of Southern California, Hubble had been cataloging the distances and velocities of galaxies for years. Mount Wilson housed the most powerful optical instrument on Earth at the time, a 100-inch reflector. That telescope had already revealed something extraordinary. The fuzzy patches astronomers called nebulae were in fact entire galaxies, each containing billions of stars. Each galaxy sat separated from the Milky Way by distances so vast that light needed millions of years to cross the gap. A pattern emerged from the data, unmistakable and clean. The farther a galaxy was from Earth, the faster the galaxy was moving away, linear. Double the distance, and the velocity doubled in lockstep. Triple the distance, triple the velocity. Space was not standing still. Space was stretching, carrying every galaxy with the fabric like raisins in rising bread dough. Distance and velocity, taken together, gave cosmologists a rate of expansion. Divide the velocity of recession by the distance, and the result is a number now called the Hubble constant. That number tells you how fast the universe is growing. And if you run the number backward, reversing the expansion like rewinding a film, the number tells you when the expansion started. The number gives you the age of the universe. Hubble calculated the constant. The number was enormous. 530 kilometers per second for every megaparsec of distance, a unit astronomers use for the gaps between galaxies. To put that in perspective, the modern accepted value is roughly 67. The Hubble number was nearly 8 times too large, and the age that enormous number implied was a disaster. According to the original measurement, the universe was roughly 2 billion years old. The problem was obvious, immediate, and devastatingly public. Geologists had already established, through radiometric dating of rocks on Earth, that the planet was at least 3 billion years old, and probably closer to 4.5 billion. By the math, the universe was younger than the ground, beneath the feet of the person doing the calculation. Younger than the rocks, younger than the planet itself. The container was younger than the contents, which is like saying a house was built decades after the furniture inside the house had already arrived. Nobody could explain the discrepancy. This measurement was not hidden in an obscure footnote or buried in a preliminary report. Hubble had published the result in one of the most visible journals in astronomy, the Proceedings of the National Academy of Sciences. Every cosmologist on Earth could see the number, and every cosmologist on Earth could see the problem. The entire expanding universe framework, the theoretical backbone of modern cosmology, rested on a number that contradicted basic geology. Worse, the contradiction was not subtle. According to the measurement, the universe was roughly half the age of the Earth. Depending on which geological estimates you trusted, the factor stretched towards 7. In 1936, Hubble stood before an audience of the National Academy of Sciences in Washington and presented the data again. 7 years had passed, yet the number had not moved, and the implications had not softened. Hubble acknowledged the tension publicly but offered no resolution. The audience listened. The press reported the measurement without irony, and the field carried the embarrassment forward, year after year, decade after decade. Picture a physician who cannot explain why the patient should already be dead, but who insists the patient is real. Consider what this meant for the people working inside the framework. Every cosmologist who believed the expansion was real also knew the expansion rate said the universe should not exist. Not in a form old enough to contain the rocks beneath the observatory, the theory was predicting an impossibility. And yet, the theory also predicted the velocities of the galaxies with precision. The pattern was too clean, too consistent, too well matched to the general relativistic models Lemaitre and others had constructed. Something was wrong with the number, but nobody could identify what. Distance. That was the source of the error, though decades would pass before anyone proved the case. Hubble measured the gaps between galaxies using a class of stars called Cepheid variables, cosmic lighthouses. These stars pulse with a regular rhythm, and the speed of the pulse reveals the true brightness. Compare true brightness to observed brightness, and the difference reveals the distance. Elegant, and devastatingly sensitive to calibration errors. But the calibration was wrong. Hubble did not know, and could not have known with the instruments available at Mount Wilson, that Cepheid variables fell into 2 distinct populations. 2 families. Population. 1 Cepheids, found in the spiral arms of galaxies, are systematically brighter than population. 2 Cepheids, found in older globular clusters. Hubble had calibrated the distance ladder using population 2 stars, then applied that calibration to population 1 stars in distant galaxies. Every distance Hubble measured was too short. Every galaxy was farther away than the data said. And because the expansion rate is velocity divided by distance, making every distance too short inflated the expansion rate, which compressed the implied age. Correction arrived in 1952. An astronomer named Walter Baade, working at the same Mount Wilson Observatory where Hubble had done the original work, used the newly completed 200-inch Hale telescope on Palomar Mountain. Baade aimed the instrument at the Andromeda Galaxy and resolved the galaxy in unprecedented detail. Baade had an advantage Hubble never had. During the Second World War, blackout conditions over Los Angeles had darkened the skies above Mount Wilson, and Baade had used those dark skies to photograph Andromeda with extraordinary clarity. What the images revealed was what Hubble could never have seen. The Cepheid variables in Andromeda belonged to a different luminosity class, one far brighter than the calibration stars in the Milky Way. Every measured distance was wrong, and not slightly wrong. Wrong by a factor of more than 2. What followed was immediate and cascading. If the distances doubled, the expansion rate halved, and if the expansion rate halved, the implied age doubled. Overnight. the 2 billion-year embarrassment became a 4 billion-year relief, and rocks on Earth were no longer older than the cosmos. But the Bardet correction was only the first revision. Over the following decades, refinements to the cosmic distance ladder, improvements in Cepheid calibration, new distance indicators like Type 1a supernovae, corrections for interstellar dust pushed the Hubble constant downward again and again. By the 1960s, the constant had dropped from 530 to roughly 100, and the implied age jumped from 2 billion years to more than 10 billion. Finally, comfortably, the container was older than the contents. Today, the accepted age of the universe stands at 13.8 billion years. Getting from 2 billion to 13.8 billion took half a century. Every single revision along the way was a quiet admission that the original number had been spectacularly wrong. But consider what had happened. For more than 20 years, from 1929 until 1952, the most important number in cosmology was wrong by a factor of 7. Not a small error, and not a rounding issue. Far beyond any matter of decimal precision. 7. A factor of 7. The entire framework of the expanding universe rested on a measurement, one that said the universe should not exist, because the universe was younger than the objects the universe contained. And the scientific community did not abandon the framework. The community held on year after year, waiting for the error to reveal itself, betting that the theory was correct and the ruler was broken. That bet paid off. But the cost of being right was 2 decades of professional embarrassment. An embarrassment that shaped the culture of cosmology forever. Young researchers who entered the field during the 1930s and 40s built entire careers under the shadow of a number that made the enterprise look foolish. Conference presentations about the expansion always carried an unspoken asterisk. The age problem haunted every conversation. Opponents like Hoyle pointed to the discrepancy as proof that the expanding universe was nothing more than a fantasy and that the steady-state model was the only logically coherent picture. For 23 years, those opponents had a point. When the correction finally came, nobody celebrated, because the correction did not erase the humiliation. Instead, 2 decades of embarrassment were transformed into something useful. Living with a wrong number for that long taught the field a lesson, one that would echo forward through every future crisis in cosmology. A beautiful framework can produce ugly numbers. And ugly numbers do not always mean the framework is wrong. Sometimes the measurement is the liar. Sometimes the ruler is bent. And sometimes the most celebrated number in the field is the very number that needs to be thrown away. And through every correction, the name followed. The Big Bang, coined as a sneer on a BBC broadcast, carried forward by accident into every textbook on the planet, attached permanently to a theory that nearly destroyed itself with a wrong number before the proof even arrived. The most famous phrase in science was coined by the theory, greatest enemy. Meanwhile, the most celebrated measurement of the theory, most fundamental prediction, was wrong by a factor that should have buried the entire idea. A name born from a lie, a number born from an error. And the story everyone believed, the comfortable, settled, familiar story of the beginning, was falling apart before the evidence had even arrived. But evidence did arrive, and the arrival was stranger than the theory itself. The proof did not come from the people anyone expected, nor from the observatories, the theorists, or the cosmologists who had spent decades fighting over the numbers. Instead, proof came from a pair of telephone engineers in New Jersey who were trying to eliminate static from a satellite dish. Those engineers had no idea what they had found, and the discovery arrived alongside the droppings of a pigeon. Picture a telephone, not a smartphone. A rotary telephone, black and heavy, bolted to the wall of a laboratory in New Jersey. That telephone is about to deliver the most important scientific result of the 20th century. Not to a cosmologist or a theorist with decades of training, to a pair of radio engineers who had spent months trying to fix a broken antenna. The year was 1964. Arno Penzias and Robert Wilson worked at Bell Telephone Laboratories in Holmdel, New Jersey. Bell Labs was not a university. Bell Labs was a corporate research center built to improve telephone communication, and the antenna Penzias and Wilson had inherited was a piece of Cold War surplus. The horn-shaped dish, 20 feet long and mounted on a rotating platform, had been designed to receive signals bounced off the Echo balloon satellite, one of the earliest American experiments in satellite communication. The satellite program was part of a larger race, a technological contest between superpowers, one that funneled billions of dollars into engineering projects the public barely understood. When the Echo program ended, the antenna sat unused on a hilltop in rural New Jersey, surrounded by farmland and silence. Penzias and Wilson saw an opportunity. The horn was the most sensitive radio receiver on Earth at the time, equipped with a cold load cooled by liquid helium to suppress thermal interference from the detector. Both engineers wanted to repurpose the instrument for radio astronomy, mapping the faint signals arriving from beyond the Milky Way. The corporate mandate was telephone research, but both men had ambitions that reached far beyond the next generation of satellite communication, and the antenna was caught between those two competing purposes. But the antenna had a problem, a persistent hiss, a low, steady noise that should not have been present, a signal with no obvious source and no obvious explanation. Every instrument produces some level of background noise, thermal interference from the electronics, stray signals from nearby cities, radiation leaking from the atmosphere above. Penzias and Wilson had accounted for all of those sources. Working methodically, the pair built a meticulous noise budget, tallying every known contribution, and the numbers did not add up. The measured signal exceeded the expected signal by a small but stubborn margin. That excess arrived from every direction in the sky, day and night, summer and winter, with a temperature of roughly 3.5 degrees above absolute zero, 3.5 degrees Kelvin. Not silence, not static, a real signal, uniform and persistent, a presence that refused to disappear, no matter how carefully the two engineers calibrated the equipment. Penzias and Wilson did what any good engineers would do. The two men started eliminating every possible source of contamination. First, the pair checked the electronics. Next, the two men rebuilt the connections between the antenna and the receiver. Then they pointed the horn at New York City to see if urban radio noise could account for the signal. New York was not the source. Rotating the antenna away from the galactic plane, the engineers tested whether radio emissions from the Milky Way were responsible. The galaxy was not the source. Even residual radiation from nuclear weapons testing, atmospheric tests that had scattered radioactive debris into the upper atmosphere during the previous decade, came under suspicion. The weapons were not the source. Months passed without resolution. The signal remained constant and isotropic, unmoved by season, direction, or time of day. Then the engineers found the pigeons. A pair of pigeons had nested inside the throat of the horn antenna, and the birds had coated the interior surface with droppings, a white layer of what Penzias later described, with scientific understatement, as a white dielectric material. Dielectric materials absorb and re-emit radio energy. Those droppings could theoretically produce a low-level thermal signal. Penzias and Wilson captured the pigeons, placed the birds in a box, drove the box 30 miles inland, and released the pigeons into the wild. The pigeons flew back. Homing instinct. So the engineers captured the pigeons a second time. Every dropping was scraped from the antenna by hand, every surface cleaned, every reflective panel polished until the interior of the horn gleamed. With the receiver reassembled, the engineers turned the instrument back on. The hiss was still present. 3.5 degrees, everywhere, all the time. Penzias and Wilson had eliminated every terrestrial explanation and one ornithological explanation, and the signal had not moved by a fraction of a degree. The two engineers have no theory to explain what the antenna was detecting, no framework, no hypothesis. That persistent noise was simply a problem that would not go away, an embarrassment that threatened to undermine the credibility of every future observation. Reluctantly, the two men wrote up a short internal report, acknowledged the unexplained excess, and filed the document with their supervisors. For months, the signal sat unexplained. Hold that thought for a moment, because 40 miles southwest, at Princeton University, a team of physicists was racing to find the exact signal that Penzias and Wilson, 40 miles away, were trying to eliminate. Robert Dick, a physicist at Princeton, and assembled a small group. Peter Rowe and David Wilkinson, both experimentalists, and a young theorist named Jim Peebles. Dickey was not a newcomer to the problem. For years, the physicist had been thinking about the thermal history of the early universe, and Dickey understood a fact that almost nobody in the wider astronomical community had remembered. 17 years earlier, a prediction had been made. A prediction so specific, so testable, and so profoundly important that the prediction should have reshaped the entire field of cosmology the moment the prediction was published. Instead, the prediction had been forgotten. George Gamow, a Ukrainian-born physicist working at George Washington University in the United States, had recognized a remarkable consequence of the expanding universe. If the cosmos was expanding now, and if the expansion was traced backward in time, then the early universe must have been unimaginably hot and dense. In those first moments, the temperature would have been so extreme that matter could not form stable atoms. Protons, neutrons, and electrons would have existed as a superheated plasma, a blinding fog so thick that light could not travel through the material. Photons would bounce from particle to particle, trapped inside a wall of charged matter, unable to escape. The universe in those earliest epochs was opaque, not dark, opaque, filled with light that could not go anywhere. But as the universe expanded, the plasma cooled, and at some point, roughly 380,000 years after the beginning, the temperature dropped below approximately 3,000 degrees Kelvin. At that threshold, a transition occurred. Electrons, which had been moving too fast for protons to capture, finally slowed enough to fall into orbit around hydrogen nuclei. Atoms formed. And for the first time in the history of the cosmos, light was free. Photons that had been trapped for hundreds of thousands of years suddenly had nowhere to bounce. The fog cleared. Light streamed outward in every direction, carrying a snapshot of the universe at the precise moment the fog lifted. Cosmologists now call that moment recombination, the epoch when electrons and protons combined for the first time to form neutral hydrogen. A misleading name since protons and electrons had never been combined before, but the name endured. Gamow and his student Ralph Alpher calculated what that ancient light should look like today. The prediction was specific. Over billions of years, the expansion of the universe would stretch those original photons, shifting the wavelengths from visible light into the microwave range, cooling the radiation from thousands of degrees to just a few degrees above absolute zero. Gamow and Alpher estimated a temperature of roughly 5 degrees Kelvin. Published in 1948, the prediction appeared in a paper that also carried the name of Hans Bethe, added by Gamow as a joke, so the author line would spell out Alpha, Bethe, Gamow, a play on the first 3 letters of the Greek alphabet. The humor obscured the importance. A faint, uniform glow, filling all of space, arriving from every direction, the leftover heat of a universe that was once too hot for light to travel. That prediction was one of the most consequential calculations in the history of physics, and the prediction was ignored. No one rejected the prediction. Not a single scientist challenged or debated the calculation at conferences. No rival paper attempted to dismantle the reasoning. The prediction was simply overlooked. The cosmological community was consumed by other arguments: the age discrepancy, the rivalry between expanding and steady-state models, the messy business of calibrating distances to faraway galaxies. Gamow's prediction gathered dust. For 17 years, the most testable consequence of the Big Bang framework sat unread in the archives, while the field argued about whether the universe had a beginning at all. Now Dick, at Princeton, had independently arrived at the same conclusion. The ancient glow should exist. A temperature of just a few degrees above absolute zero should permeate the sky. And Dickey wanted to find the signal before anyone else did. Roland Wilkinson were building a detector on the roof of Palmer Physical Laboratory, a Dickey radiometer designed specifically to measure faint microwave radiation from the sky. Modest in size compared to the Bell Labs horn, the instrument was a cone-shaped antenna, precisely calibrated for the frequency range where the primordial glow should be strongest. Nearly complete, the detector awaited only final adjustments. The race was almost over. Then the telephone rang. A mutual colleague, the radio astronomer Bernard Burke at the Massachusetts Institute of Technology, had recently spoken with Penzias about the persistent noise problem. Burke also knew about the Princeton group, recognizing that the unexplained signal at Bell Labs might be exactly what Dickey sought. The radio astronomer called Penzias and told Penzias to contact Robert Dickey at Princeton. Penzias picked up that heavy black rotary telephone and dialed. Dicker was eating lunch with Roll, Wilkinson, and Peebles in a small office when the call arrived. Penzias described the signal in precise detail, a persistent excess of 3.5 degrees, uniform across the entire sky. Isotropic, present in every direction, at every hour, in every season. Dickey listened carefully. When Dickey hung up the telephone, Dickey turned to the 3 colleagues around the lunch table and said 5 words that entered the permanent record of science. "Well, boys, we have been scooped." The most important cosmological discovery of the 20th century had been made by 2 telephone engineers who did not even know what the discovery was. The Princeton team, the group that understood the prediction, the group that was building a purpose-designed detector on the roof of the physics building, the group that had independently derived the theory, arrived moments too late. Penzias and Wilson had stumbled onto the leftover heat of creation while trying to fix what the 2 engineers believed was a malfunction in the instrument. The hiss was not a malfunction. The hiss was the oldest light in the universe, a relic of the moment when the cosmos cooled enough for photons to escape. Consider what the cosmic microwave background actually represents. What Penzias and Wilson detected is not a signal from a star, a galaxy, or any single object in the sky. That glow is the afterimage of a moment when the entire observable universe was a single, blinding fog. Every photon in that glow has been traveling for 13.8 billion years, stretching as the cosmos expanded, cooling from thousands of degrees to 2.725 degrees Kelvin. Right now, as these words reach your ears, that ancient light is passing through your body. Those photons are everywhere, not concentrated in one part of the sky, everywhere. Turn a radio telescope to any direction, any angle, any point on the celestial sphere, and the signal is present. Older than any star, older than any galaxy, older than every structure that has ever formed in the history of the cosmos, the cosmic microwave background is the oldest observable phenomenon in the universe. And the glow was found by accident, by 2 men scraping bird droppings off a surplus military antenna, while the trained cosmologists who understood the significance were still assembling the instrument on a nearby rooftop. Dickey, Peebles, Roll, and Wilkinson drove to Holmdel to examine the Bell Labs data firsthand. After inspecting the antenna, reviewing the noise budget, and confirming the detection, the Princeton team reached a verdict. The measured temperature matched the theoretical prediction within the uncertainties of the instruments. The signal was real. 2 papers were prepared and submitted to the Astrophysical Journal, arranged to be published back-to-back in the same issue. The first, by Dickey, Peebles, Roll, and Wilkinson, explained the cosmological significance of a cosmic background radiation, providing the theoretical context and the prediction that such a glow must exist if the universe began hot and dense. By contrast, the second paper, by Penzias and Wilson, bore a title so modest the title almost concealed the magnitude of what had been found. A measurement of excess antenna temperature at 4,080 megacycles per second. Excess antenna temperature, the most revolutionary observation in the history of cosmology, described in the language of troubleshooting and calibration. Nowhere in the title did the words universe, creation, Big Bang, or cosmology appear. In 1978, Penzias and Wilson received the Nobel Prize in Physics. Gamow, who had predicted the existence of the glow 17 years before anyone detected the glow, received nothing. Gamow had died in 1968, a full decade before the prize was awarded, and the Nobel Committee does not honor the deceased. The man whose calculation made the discovery possible, the physicist who had described the relic glow of the Big Bang with startling accuracy, never witnessed the recognition. Alpha, who had co-authored the prediction and spent years being overlooked, lived until 2007. Alpha received honorary degrees and belated acknowledgement, but never the Nobel. But the discovery accomplished a transformation far larger than awarding prizes or settling decades of academic argument. Detection of the cosmic microwave background destroyed the steady-state universe. Fred Hoyle, the man who had coined the phrase Big Bang as an insult on BBC Radio, the physicist who had championed an eternal cosmos with no beginning and no end, now faced a problem that no amount of brilliance could resolve. Under the steady-state model, the universe should look the same at every epoch. No beginning meant no primordial heat. No primordial heat meant no leftover glow. And yet the glow was present, measured, confirmed, arriving uniformly from every direction in the sky at precisely the temperature an expanding, cooling universe would produce. That glow was a fossil, a relic of a moment when the cosmos was young and hot and opaque. An eternal universe has no room for such a fossil because an eternal cosmos produces no childhood relics. An eternal universe has no childhood. Hoyle fought the result for years. Hoyle proposed alternative mechanisms, arguing that starlight scattered off interstellar dust grains might mimic a thermal background. None of the alternatives survived scrutiny, but the spectrum of the glow was the decisive test. A true thermal source produces radiation that follows a precise mathematical curve called a blackbody spectrum. In 1990, the Cosmic Background Explorer satellite, known as COB, measured the spectrum of the microwave background with extraordinary precision. What emerged was a perfect blackbody, matching the theoretical curve to better than 50 parts per million. When John Mather presented the COB spectrum at a meeting of the American Astronomical Society, the audience gave the result a standing ovation. So clean, so perfectly thermal, the curve left no room for doubt. No scattering process and no collection of dust grains could reproduce the shape. The glow was real, ancient beyond measure. And that ancient light meant the universe had a past. The man who named the Big Bang as a joke had been proven wrong by a signal that arrived from the earliest epoch of the cosmos, detected by engineers who were not searching for the signal, predicted by a physicist whose prediction had been forgotten for nearly 2 decades, confirmed by a team that had been building the right instrument in the right place at the right time and still arrived too late. The proof of the universe's fiery past materialized through a chain of accidents, oversights, and missed connections so improbable, the sequence reads less like science and more like a parable about humility. And yet the story does not end with wonder. The proof that arrived through pigeon droppings was not flawless. The cosmic microwave background confirmed that the universe was once hot, dense, and opaque. That confirmation also proved the expansion was real and the steady-state model was dead. 3 pillars of the Big Bang framework now stood firm. First, the expansion, measured through the recessional velocity of galaxies receding in every direction. Second, the ancient glow. And a third pillar, one that had been in place even before the glow was detected. A recipe, a prediction about what elements should exist in the universe, cooked in the opening minutes after the beginning, forged from raw protons and neutrons in a furnace that lasted less than 20 minutes. That recipe had passed every test for 3 elements: hydrogen, helium, and deuterium, the rarest of the 3. The lightest building blocks, assembled in the first moments when the universe was hot enough for nuclear fusion, but cool enough for the products to survive. Across 9 orders of magnitude, predicted abundances matched observed abundances with extraordinary precision. 3 ingredients, 3 matches, 3 confirmations spanning a range so vast, the agreement ranked among the most successful quantitative predictions in the history of physics. Encoded in the ratios of elements, the universe had kept a record of the first 20 minutes, and the record matched the theory perfectly. But a 4th ingredient existed, and a 4th ingredient did not match. The recipe predicted a specific amount of lithium-7, the lightest metal, forged alongside hydrogen and helium in those first frantic minutes of nucleosynthesis. The predicted abundance was 3 times higher than what astronomers measured in the oldest, most pristine stars in the galaxy. Not slightly off, not within the margins of experimental uncertainty. 3 times too high, a factor of 3 that no calibration error could explain. The most precisely tested theory in the history of cosmology. The theory, rescued from decades of humiliation by two engineers and a flock of pigeons, now carried a crack, a single number, stubbornly and persistently wrong, sitting at the base of the framework, like a hairline fracture in a wall that bears the weight of everything above. Nobody could explain the discrepancy. Astronomers proposed that the oldest stars might have destroyed some primordial lithium through internal mixing, dragging surface lithium down into hotter layers, where nuclear reactions would break the atoms apart. But the models of stellar mixing could not account for the full factor of 3, and the most metal-poor stars, the ones that should most closely preserve the primordial composition, showed the same deficit. Nuclear physicists proposed that the reaction rates used in the nucleosynthesis calculations might contain errors, that the cross-sections measured in laboratories might not perfectly represent conditions in the first minutes. But repeated experiments at particle accelerators confirmed the reaction rates to high precision, and the discrepancy remained. Some theorists proposed new physics, exotic particles that might have altered the neutron-to-proton ratio in ways that suppressed lithium production. None of those proposals have been confirmed. The crack has been open for decades, open still today. A beautiful recipe, perfect for 3 elements, broken for 1. And the question that follows, the question the crack demands, will not let the story rest. If one number is wrong, what else might be wrong? That question needs a real answer, not a reassurance, not a dismissal, a genuine look at the recipe itself from the inside out. Because a theory that predicts the composition of the universe with staggering accuracy can also carry a flaw that nobody has been able to repair. Because the recipe is real, and the recipe is extraordinary. Before examining the crack, the full scale of what the elemental forging accomplished needs to sit in the open, exposed to the same scrutiny as the failure. Otherwise, the crack looks like a curiosity. The crack is not a curiosity. The crack is a wound in the most successful quantitative prediction in the history of science. Start with the setup. 1 second after the beginning, before a single atom existed, the universe was a superheated fog of particles. Protons, neutrons, electrons, photons, neutrinos, all colliding billions of times per second, all moving at close to the speed of light, roughly 10 billion degrees. At that temperature, matter cannot hold together. Any attempt by a proton and a neutron to bond is shattered by the surrounding radiation. Photons slam into the fragile bond and break the pair apart before the nucleus survives a trillionth of a second. The universe at 1 second old was too hot for chemistry, too violent for structure, too energetic for anything permanent to exist. But the universe was expanding. And expanding means cooling. Every fraction of a second, the temperature dropped. The collisions grew slightly less violent, and the window for nuclear fusion inched closer to opening. The key players were neutrons and protons, locked in a ratio set by the physics of the weak nuclear force. When the weak interactions could no longer keep pace with the expansion, the ratio froze at roughly 1 neutron for every 5 protons. But free neutrons kept decaying. By the time fusion began, several minutes later, the count had dropped to 1 neutron for every 7 protons. That ratio, at the onset of fusion, matters more than almost any other number in the history of science because everything that follows depends on the starting ingredients. Change the ratio by even a small amount, and the entire chemical composition of the universe shifts. More neutrons would mean more helium and less hydrogen. Fewer neutrons would mean the opposite. The universe was cooking, and the proportions of the ingredients had already been locked in place by the interplay between expansion and the forces governing particle decay. Meanwhile, free neutrons were dying. Unbound neutrons are unstable. Left alone, a neutron decays into a proton, an electron, and an antineutrino, with a mean lifetime of roughly 880 seconds, a little under 50 minutes. The clock was ticking. Every second that passed between freeze-out and the onset of fusion meant fewer neutrons available for the recipe. The universe had a narrow window, and the window was closing. Too hot, and the bonds would not hold. Too cold, and the neutrons would all have decayed into protons before the cooking could begin. The timing had to be precise. Not designed, not planned, simply a consequence of physics, playing out in a universe that had no obligation to produce anything interesting at all. Around 3 minutes after the beginning, the temperature dropped to roughly 1 billion degrees, still incomprehensibly hot by any terrestrial standard, but cool enough for a specific event to occur. A proton and a neutron collided and stayed together. The bond held. A deuterium nucleus, the simplest compound nucleus in existence, survived the surrounding radiation for the first time. One proton, one neutron, fused into a single object heavier than either ingredient. The deuterium bottleneck had broken. The bottleneck deserves a moment of attention because the bottleneck is the reason the recipe exists at all. Deuterium is fragile. The binding energy of a deuterium nucleus is only 2.2 megaelectron volts, modest compared to the energies of the photons flying through the plasma. Even after the universe cooled below the deuterium binding energy, the sheer number of photons, outnumbering baryons by more than 1 billion to 1, meant that the high-energy tail of the photon distribution could still shatter deuterium faster than collisions could form new nuclei. The bottleneck held until the photon temperature dropped far enough below the binding energy so that the destruction rate finally fell behind the creation rate. Only then did deuterium begin accumulating in meaningful quantities, and only then could the cascade of heavier element production begin. The cascade arrived fast. Deuterium nuclei collided with protons and formed helium-3. Deuterium collided with other deuterium and formed helium-3 plus a free neutron, or tritium plus a free proton. Tritium collided with deuterium and formed helium-4, the stable 2-proton, 2-neutron configuration that would become the second most abundant element in the cosmos. All of these reactions happened simultaneously, in a plasma expanding and cooling so rapidly that the entire process lasted less than 20 minutes. By the time the universe was 20 minutes old, the nuclear furnace had shut down. Temperatures had dropped below the threshold for fusion. Expansion won, and the cooking was over. And the cooking could not resume. A critical fact about the periodic table, one that no amount of heat or pressure could override, sealed the outcome forever. No stable nucleus exists with a mass number of 5, and none exists with a mass number of 8. Nature had placed a wall across the periodic table. The wall stood at exactly the point where complexity would have demanded a bridge. Helium-4, with mass number 4, is extraordinarily tightly bound. But the next step up, 5 nucleons, falls apart instantly. And 8 nucleons, the product of fusing 2 helium-4 nuclei together, is beryllium-8, which disintegrates in less than 1/trillionth of a second. Without a stable stepping stone at mass 5 or 8, the nuclear reactions had no pathway to build carbon, oxygen, or anything heavier. Stars would eventually find a way around the bottleneck through the triple alpha process, but that process requires the sustained high density of a stellar core, a density the rapidly expanding universe could never maintain. The primordial furnace was a sprinter, not a marathon runner. 20 minutes. Done. And the universe had written a recipe, not a metaphorical recipe. A literal, testable, falsifiable prediction encoded in the relative abundances of the lightest elements, waiting billions of years for someone to decode the numbers. The first person to attempt the decoding was George Gamow. In the 1940s, Gamow and his doctoral student Ralph Alpher at George Washington University recognized that the expanding, cooling universe implied a specific sequence of nuclear reactions in the first minutes, and that the sequence would leave behind a predictable distribution of light elements. Alpher's doctoral dissertation, published in 1948, laid the groundwork for the entire field of primordial element forging. Crude by modern standards, the calculation was missing. Key processes like the weak interactions that govern neutron decay and the nuclear cross-sections were approximations. But the central insight was correct. An early universe, governed by known physics, behaved as a nuclear reactor whose output could be calculated. Over the following 2 decades, Robert Wagner, William Fowler, and Fred Hoyle refined the calculations, incorporating measured reaction rates from laboratory experiments. By the late 1960s, the prediction had sharpened into a quantitative framework. Given the baryon density, the nuclear physics produces a specific set of abundances, no free parameters beyond that single density. The prediction was ready to be tested against the sky. And the sky, remarkably, cooperated. But understanding what the sky was saying required looking at the products one at a time. Each element demanded a different measurement technique, a different class of astronomical target, and a different set of systematic uncertainties. What emerged between prediction and observation across the decades is not a single number. The agreement is a web of independent measurements conducted by different teams using different instruments pointed at different objects, all converging on the same conclusion. Hydrogen, the most abundant product by an enormous margin, roughly 75% of all baryonic matter by mass. Helium-4, roughly 25%, a quarter of all ordinary matter in the cosmos, manufactured in less than a third of an hour. Deuterium, a trace amount, roughly 25 parts per million relative to hydrogen. Helium-3, an even smaller trace. And at the very bottom of the abundance ladder, lithium-7, the lightest metal forged in the tiniest quantities, barely a footnote in the cosmic inventory. Those 5 products and the precise ratios between the products constitute the prediction. What the calculation predicts is not simply that the universe should contain some hydrogen and some helium. Rather, hydrogen and helium should appear in a ratio of approximately 3:1 by mass, with deuterium at a specific abundance that depends on the baryon to photon ratio, and helium-3 at a specific abundance that depends on the same ratio, and lithium-7 at a specific abundance that also depends on the same single number. One free parameter, one dial. Turn the dial, and all 4 abundances shift together, locked in a web of nuclear physics so tight that changing any single reaction rate by a meaningful amount would break the agreement for all the remaining elements. One number controls the entire framework. The baryon to photon ratio describes how many baryons, protons, and neutrons exist for every photon in the universe, approximately 6 times 10 to the negative 10th power. 6 baryons for every 10 billion photons, a staggeringly small number, which means the universe is overwhelmingly made of radiation, and ordinary matter is a trace contaminant in a sea of light. That single number, measured independently from the cosmic microwave background, pins the entire prediction to a wall. No wiggle room, no tuning. Baryon density tells you the temperature evolution. Temperature evolution tells you the reaction rates. Reaction rates tell you the abundances. A chain of logic so clean that the output is not an estimate, but a hard number. The uncertainty bars are so small that any deviation from observation would signal either a measurement error or a crack in the foundation physics. And the prediction works. For 3 elements, the prediction works with precision that borders on the absurd. Deuterium, the fragile isotope, easy to destroy and impossible to create in significant quantities after the first 20 minutes. Any deuterium that exists today must be primordial because stars burn deuterium, and stars do not make deuterium. Astronomers measure deuterium in ancient gas clouds, backlit by distant quasars, where the light of the quasar passes through pristine hydrogen, hydrogen that has never been inside a star. Extraordinary precision is required. An astronomer must identify absorption features in the quasar spectrum, features that correspond to deuterium rather than hydrogen. The astronomer must then distinguish between the 2 isotopes, separated by a tiny wavelength shift, and correct for contamination by unrelated gas along the line of sight. Despite those challenges, the measured abundance matches the prediction. Not roughly, not within an order of magnitude, within the error bars, across 9 orders of magnitude in the abundance scale, from the lightest elements to the heaviest products of the first forging. The predicted and observed deuterium abundances align to a degree that makes most physicists uncomfortable with how well the agreement holds. Helium-4, the workhorse product, manufactured in enormous quantities during those 20 minutes. Astronomers measure helium in the most chemically primitive regions of the universe, low metallicity dwarf galaxies where star formation has barely begun, where the helium abundance most closely reflects the primordial composition. By studying emission lines from ionized gas in star-forming regions, extracting the helium to hydrogen ratio, and then extrapolating backward to 0 metallicity, astronomers estimate the helium abundance before any stars had enriched the gas. Measured mass fraction, approximately 0.245. The predicted mass fraction from the calculation, approximately 0.247. Agreement to within a fraction of a percent. A prediction made from nuclear physics and the expansion rate of the universe, confirmed by telescopes pointed at galaxies billions of light years away. Helium-3, the rarest of the three successes, measured in the interstellar medium of the Milky Way and in planetary nebulae. Observed abundance is consistent with predicted abundance, though the uncertainties are larger than for deuterium or helium-4. Agreement holds 3 for 3. 3 elements manufactured in a window shorter than a lunch break, predicted by equations written decades before the measurements were possible, confirmed by instruments pointed at objects billions of light years away. The universe kept a record of the first 20 minutes, and the record matched the theory with a precision that has no parallel in any other branch of science. Now consider what the full picture means. A theory built from the physics of the first 20 minutes, calibrated by a single number derived from a completely independent measurement of the oldest light in the universe, predicts the chemical composition of the cosmos across 9 orders of magnitude. 3 elements, 3 matches, an alignment so precise across such an enormous range of abundances that no other quantitative prediction in any branch of science has matched the achievement. The recipe for the universe, written in the first third of an hour, stored in the ratios of elements scattered across billions of light years of space, still legible 13.8 billion years after the cooking ended. No other theory in science makes a prediction this precise, this testable, and this resoundingly confirmed. And still, the recipe predicted a 4th ingredient. The 4th ingredient does not match. Lithium-7, the lightest metal, forged in trace quantities during those same 20 minutes through a chain of reactions involving tritium and helium-4, helium-3 and helium-4, and the subsequent decay of beryllium-7 into lithium-7 over the centuries following the elemental forging. The predicted abundance, pinned by the same baryon-to-photon ratio that nailed deuterium and helium, is approximately 3 times higher than what astronomers observe. Not slightly higher, not within the generous bounds of experimental uncertainty. 3 times too high. A clean, hard factor of 3. The measurement comes from the oldest stars in the galaxy. In 1982, 2 French astronomers working at the Paris Observatory, François Spiet and Monique Spiet, published a result that would haunt cosmology for decades. Together, the husband and wife team had been studying the atmospheres of ancient stars. Those stars orbit in the halo of the Milky Way. Metal-poor halo stars, objects so old and so chemically pristine that the composition of the stellar atmospheres should reflect the primordial abundances. Elements cooked in those first 20 minutes had been preserved in the outer layers of stars. Those stars formed before the galaxy had time to pollute the surrounding gas with heavier elements from supernovae and stellar winds. François and Monique focused on the warmest, most unevolved stars in the sample, choosing targets where the convective zone, the churning outer layer that mixes surface material with deeper and hotter regions, was thin enough that primordial lithium on the surface would not have been dragged down and destroyed. What the Spiet team found was striking. Among those carefully selected halo stars, the lithium abundance was constant. Star after star, regardless of temperature, regardless of metallicity, regardless of distance from the galactic center, showed the same lithium abundance, a flat line on a graph, a plateau, not a scatter and not a descending trend. A clean, horizontal feature sitting at a single value across a wide range of stellar properties. Soon, the Spiet plateau became one of the most discussed features in observational astrophysics. A constant value, independent of the properties of the star, suggested that the measured abundance was not a product of stellar evolution. What those stars preserved was a fossil, a relic of the first 20 minutes, frozen in the atmospheres of stars that had never mixed the primordial material deep enough to destroy the lithium through nuclear burning. The Spiet plateau was, by all appearances, the primordial lithium abundance of the universe. And the primordial lithium abundance was 3 times too low. The implication landed immediately. If the Spiet plateau represented the true primordial value, then the prediction had a problem. Not a vague, hand-waving problem buried in approximations. A clean, hard, numerical disagreement between a measurement and a calculation, both conducted with care, both repeated by independent groups, both pointing in the same direction. The prediction said the universe should have produced more lithium-7 than the oldest stars contain. An unknown mechanism had either destroyed the lithium after the fact, or an unknown flaw in the calculation was producing the wrong number. For nearly 2 decades, the discrepancy remained uncertain. Neither the baryon to photon ratio nor the lithium measurement was known precisely enough to sharpen the comparison. Error bars on both sides were wide enough that overlap between prediction and observation could not be ruled out. Most cosmologists acknowledged the tension, but treated the tension as provisional. Perhaps improved measurements on either side would close the gap. Then the gap became a wall. In 2001, the Wilkinson Microwave Anisotropy Probe launched from Cape Canaveral, Florida, aboard a Delta II rocket. WMAP was not designed to solve the lithium problem. Instead, the probe was designed to map the cosmic microwave background with unprecedented precision, measuring the tiny temperature fluctuations in the oldest light to extract the fundamental parameters of the universe. One of those parameters was the baryon density. When the WMAP team published the results, the baryon to photon ratio was pinned to a narrow range, with uncertainty so small that the predictions snapped into focus. Deuterium matched, helium matched, and lithium-7, now locked to a precise input, sat stubbornly, unmistakably, a factor of 3 above the spiked plateau. The cosmic lithium problem, as the community came to call the discrepancy, had crystallized from a vague tension into a hard, quantified failure. The discrepancy now had a name, a growing literature, and no answer. Brian Fields at the University of Illinois wrote the definitive review in 2011, cataloging every proposed solution and finding none sufficient. The cosmology community responded the way scientists respond to uncomfortable numbers. Proposals arrived from every direction. Perhaps the oldest stars had destroyed some primordial lithium after all. Convective motions inside the star might have dragged surface lithium down into hotter layers, where nuclear reactions would break the atoms apart. Atomic diffusion, the slow gravitational settling of heavier elements toward the stellar interior, might have pulled lithium beneath the observable surface over billions of years. Models of stellar mixing were constructed, tested, refined. Observations of globular clusters, groups of stars born from the same gas at the same time, showed that lithium abundances did depend slightly on temperature and luminosity, suggesting that some depletion had occurred. But the corrections fell short of closing the full factor of 3. Even the most metal-poor stars, the ones least likely to have altered the primordial composition, showed the same deficit. Still, the plateau did not bend. Against every adjustment and every correction, the plateau held firm and flat. So nuclear physicists proposed an entirely different class of explanation. Perhaps the reaction rates used in the calculations contained errors, and the laboratory measurements did not perfectly capture the conditions of the first minutes. Teams at particle accelerators in Europe, Japan, and the United States remeasured the relevant reactions, particularly those involving the production and destruction of beryllium-7, the precursor that eventually decays into lithium-7. At the Lunar Underground Laboratory beneath the Gran Sasso mountain in central Italy, physicists repeated the measurements at energies closer to the conditions of the early universe, shielded from cosmic ray interference by 1,400 meters of rock overhead. Refined measurements did not help. In fact, several updated reaction rates made the discrepancy slightly worse. Particle theorists proposed yet another path. Perhaps the standard model of particle physics was incomplete. Perhaps exotic particles beyond the known inventory had altered the neutron-to-proton ratio in the first seconds, suppressing lithium production through channels that left deuterium and helium untouched. Supersymmetric particles, decaying relics from a higher energy epoch, might have injected energetic photons or hadrons into the plasma at precisely the moment when beryllium-7 was forming, selectively destroying the lithium precursor without disturbing the heavier products. Dozens of papers explored this territory, and none produced a confirmed mechanism. Those exotic particles remain undetected. At CERN, the Large Hadron Collider, the most powerful particle accelerator ever built, has found no evidence of supersymmetric partners or any other beyond standard model particles that could resolve the lithium discrepancy. No accelerator has found them. One more attempt deserves mention. In 2012, a team used a bright star in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, as a background light source to measure interstellar lithium absorption in gas that had never been inside a star. The technique bypassed the stellar depletion problem entirely, probing the lithium abundance of raw, unprocessed gas in one of the lowest metallicity environments accessible to modern telescopes. What emerged was tantalizing, but inconclusive. Measured abundance was consistent with the Spite Plateau, not with the higher prediction from the calculation. But the measurement carried large uncertainties because most of the lithium in the gas was ionized and invisible to the instrument. A neutral fraction correction was required, and that correction introduced enough ambiguity that the measurement could not decisively close the case. Elegant as the attempt was, the answer remained out of reach. And so the crack has stayed open. 4 decades have passed since the Spite Plateau was first measured. More than 2 decades since WMAP locked the baryon density. Hundreds of papers have been published. Thousands of hours of telescope time pointed at the oldest stars in the Milky Way halo. Experiments at accelerators on 3 continents have chased the answer. No resolution has arrived, and no widening either. A factor of 3 sits in the data, stable and patient, waiting for an explanation that has not come. Right now, as these words reach the ear, the lithium in the atmospheres of those ancient halo stars is still present, still measurable, still sitting at the same value that François and Monique Spicet reported more than 4 decades ago at the Paris Observatory. The prediction still says 3 times too much. Baryon density from the cosmic microwave background is still locked to the same narrow range. Nothing has moved. The discrepancy is not growing and not healing, simply there. Consider what the crack means for the framework. 3 predictions confirmed to extraordinary precision. 1 prediction derived from the same physics, using the same input parameter, governed by the same equations, fails by a factor of 3. Not vague. The failure is specific, reproducible, and stubbornly resistant to every proposed resolution. What breaks is not the entire calculation. What breaks is far more unsettling, because the recipe is almost perfect. Every ingredient matches except one, and the one ingredient that fails is the one that should be the most straightforward to predict. Lithium-7 is produced by a small number of well-understood nuclear reactions, calibrated by laboratory measurements, in a regime where the physics is supposed to be completely under control. A crack in a weak prediction would be easy to dismiss. A crack in the strongest, most precisely calibrated prediction in the history of observational cosmology is a different matter entirely. What the discrepancy reveals is not that the theory is wrong. What the discrepancy reveals is that the theory is incomplete. Somewhere in the chain, from the baryon density to the nuclear reaction network to the abundances that emerge, a piece is missing. A piece that does not affect hydrogen, does not affect helium, and does not affect deuterium, but quietly, precisely, stubbornly alters the yield of the lightest metal by a factor of 3. Nobody knows what the missing piece is. Nobody knows whether the missing piece hides in nuclear physics, in stellar astrophysics, or in the fundamental particle inventory of the universe. The possibilities are not equivalent. Should the explanation turn out to be stellar, then the cosmological framework survives untouched. The crack was never in the recipe at all, only in the container where the recipe was stored. If the explanation turns out to be nuclear, then the reaction rates governing the first 20 minutes require revision, and every abundance prediction shifts by an amount that depends on which rate was wrong. And should new physics be required, then the standard model of particle physics is incomplete, and the first 20 minutes of the universe contained ingredients that no laboratory on Earth has ever detected. Each possibility carries a different weight, and each rewrites a different chapter of physics. 4 decades have passed, the community has not closed the case. Graduate students who began their careers studying the lithium problem in the 1980s have now retired. The problem outlasted entire careers. The factor of 3 has not budged. And the stubbornness of the discrepancy points to a deeper truth about the Big Bang framework itself. the theory that predicted the elemental recipe of the cosmos with extraordinary precision. The same theory rescued by 2 engineers and a flock of pigeons in New Jersey. The same theory humiliated by a wrong distance measurement for 23 years now carries a scar. Small and specific, the scar does not threaten the life of the framework, but that scar proves the framework is not complete. Somewhere in the first 20 minutes of the universe, a process occurred that the equations do not fully capture, and the universe encoded that process in the abundance of a single element, the lightest metal on the periodic table, sitting in the atmospheres of the oldest stars, waiting for an explanation that has not arrived. 3 elements predicted with breathtaking accuracy. A 4th predicted with a persistent, unexplained error of 300%. And the question that follows, the question the lithium problem poses, in the silence between the confirmed numbers and the broken one, refuses to let the story settle into comfort. 3 elements match perfectly. 1 does not. For decades, that crack has been open, and nobody has closed the gap. If the most precisely tested prediction in the history of science is quietly and stubbornly wrong for one ingredient, then the question is no longer whether the recipe works. Because the recipe works, what remains is what the recipe is hiding. The recipe is hiding the most important secret in the history of cosmology. Not the flaw, not the crack. A revelation far larger than any single broken number. Because the entire framework, the expansion, the ancient glow, the elemental forging, every prediction and every confirmation describes what happened after the beginning, not the beginning itself. The Big Bang, the theory that carries the most famous name in all of science, does not describe what the name promises. The name promises an origin, but what the theory actually delivers is only a consequence. Hold that thought for a moment, because the distinction between the origin and the consequence is not a technicality. That distinction is a wall, a literal boundary in physics, beyond which every known equation stops working, every prediction collapses, and the universe becomes a place that no human framework can describe. And the story of how physicists discovered that wall, what the wall means, and what hides behind the barrier, is the deepest and most unsettling chapter in the entire history of the Big Bang. Start at the beginning, or rather, start at the place where the beginning should be, and watch the physics fall apart. General relativity, the framework Albert Einstein published in 1915, describes the geometry of space and time with extraordinary precision. Gravity is not a force in the Einsteinian picture. Instead, gravity is the shape of the cosmos, the curvature of space around matter, the bending of time near mass. Einstein's equations predicted the expansion of the universe before anyone observed the expansion. Those same equations predicted the bending of starlight around the sun before Arthur Eddington photographed a solar eclipse in 1919 and confirmed the prediction. For more than a century, general relativity has been tested against observation, and the framework has never been wrong. But the equations have a limit. Run the expansion of the universe backward in time. Watch the galaxies converge. Watch the space between the galaxies shrink, the temperature climb, the density soar, and the equations produce a singularity, a point where the density of matter becomes infinite, where the curvature of space becomes infinite, where the temperature reaches a value so extreme that no number is large enough to contain the result. At that threshold, the equations do not give a wrong answer. Instead, the equations give no answer at all. Mathematics breaks. Dividing by zero. A framework that predicted the orbit of Mercury, the bending of light, and the expansion of the cosmos reaches a place where the framework itself ceases to function. That place has a name, the Planck epoch. And the boundary arrives not at the beginning of time, but at a specific threshold, a specific duration after whatever happened at the start. 5.39 times 10 to the negative 44th power of 1 second. That is the threshold. Written out, that number is a decimal point, followed by 43 zeros, and then a 5. A duration so inconceivably brief that calling the duration a fraction of a second is meaningless. No physical process in the known universe operates on that timescale. Not a single particle interaction, not a single quantum fluctuation, not a single event of any kind that physicists have ever measured occurs that quickly. Beyond being merely small, the Planck time is the boundary where the concept of time, as general relativity defines the concept, may cease to have meaning. Before the Planck epoch, the universe was smaller than an atom, not a metaphor. Everything that would eventually become every galaxy, every star, every planet, every photon of the ancient glow was compressed into a volume smaller than the nucleus of a hydrogen atom. At that scale, two domains of physics collide. General relativity, governing the very large, demands that space curves smoothly and predictably. But quantum mechanics takes the opposite position. Governing the very small, quantum mechanics demands that space fluctuates wildly and unpredictably. In every other regime the universe has ever occupied, those two domains operate in separate jurisdictions. Stars and galaxies obey general relativity. Atoms and particles obey quantum mechanics. Under normal conditions, the two frameworks never need to shake hands because the two frameworks never meet. At the Planck epoch, those two frameworks collide. For the first and only time in the history of the cosmos, both frameworks apply to the same object at the same moment, and neither survives the encounter. The collision is not a theoretical curiosity. The collision is the reason nobody can describe the beginning. General relativity predicts a smooth singularity. Quantum mechanics, by contrast, predicts a roiling foam of wild fluctuations. The two predictions flatly contradict each other. Mathematics from one framework cancels mathematics from the other, and what emerges from the collision is not a prediction, but gibberish. Numbers that mean nothing, infinities that cancel other infinities and leave behind quantities that no physicist can interpret. Far from a metaphor, the wall is a mathematical boundary, as hard and as real as any barrier in physics, where the known laws of nature, tested and confirmed for a century, simultaneously demand contradictory outcomes and produce no coherent picture of reality. No confirmed theory of quantum gravity exists. Physicists have spent decades constructing candidates, and none has survived the test of experiment. String theory proposes that the fundamental constituents of reality are not particles, but vibrating filaments of energy operating in 10 or 11 dimensions, most of which are curled so tightly that no experiment can detect the extra dimensions. Loop quantum gravity proposes a different picture entirely, one where space itself is not continuous, but woven from discrete units, tiny loops of gravitational field, stitched together into a fabric that only appears smooth at large scales. Both frameworks are mathematically elegant. Yet neither has been confirmed by a single experiment. Neither has produced a testable prediction that any instrument on Earth, or in orbit, or conceivable within the next century could verify. And the wall stands. Decades of effort have not moved the boundary by a single Planck length. Graduate students who entered theoretical physics in the 1980s, hoping to crack quantum gravity, have retired without a solution. Entire research programs, funded by governments on 3 continents, have been built around the promise of unifying general relativity and quantum mechanics. No program has delivered a confirmed framework. Between the two leading candidates, string theory and loop quantum gravity, tens of thousands of papers have been published. Mathematical sophistication is staggering. Experimental verification remains at 0, and the wall remains exactly where the wall has always been, at the Planck epoch, that impossibly thin sliver of time after whatever happened at the start. Behind the wall, the origin of the universe, if such an origin exists, remains hidden, sealed off from observation, from calculation, from every tool that physics has ever produced. Consider what this means for the Big Bang itself. A theory named after the beginning does not describe the beginning. Instead, the theory describes what happens starting at a fraction of a second after the earliest moment that physics can model. 380,000 years after whatever happened, the ancient glow captures a snapshot. Meanwhile, the elemental recipe, the forging of hydrogen and helium and deuterium, records the chemistry from 3 minutes after. Billions of years later, the expansion finally becomes visible through the recessional velocity of galaxies rushing apart. consequence after consequence after consequence. Every pillar of the Big Bang framework is a record of the aftermath, not the origin, not a description of the start itself. A name that promised the beginning, a theory that delivered all of the consequences but none of the origin. And the one claim the name makes is the one claim nobody can verify. The scientific community knew the truth, not recently, not as a modern correction to an old misunderstanding. From the earliest days of the framework, the singularity at the core of the expanding universe model has been understood not as a physical event, but as a limit. A place where the model confesses that the model has nothing more to say. Georges Lemaitre, the Belgian priest and physicist who first proposed the expanding universe in 1927, understood the distinction clearly. Lemaitre called the initial state the primeval atom, a poetic name, a concept Lemaitre never claimed to explain. With mathematical precision, Lemaitre described the consequences of the expansion, but Lemaitre never pretended that the equations reached the actual origin. From the very beginning, the theory was a description of the aftermath. And the name, coined decades later as a joke by a man who hated the idea, obscured that distinction forever. But the wall at the Planck epoch is only half the story. In the 1970s and 1980s, physicists discovered that the aftermath itself was incomplete. Even setting aside the unreachable origin, the Big Bang framework could not explain the very universe that the framework was designed to describe. 3 problems emerged from the data, each more disturbing than the last, and each pointing to the same conclusion. Between the wall and the aftermath, a missing chapter existed. An enormous chapter. A chapter that the original framework had no room to contain. First came flatness, measured through the angles of distant triangles drawn across the cosmic microwave background. The geometry of the universe turned out to be flat, not curved inward like a sphere, not curved outward like a saddle. Flat. Perfectly, almost absurdly flat. And flatness in general relativity is not the default state. Flatness is a knife edge. A universe that begins even slightly curved grows more curved over time. Even a tiny deviation in the first second would have compounded across 13.8 billion years into a cosmos so curved that galaxies could never form, or so open that matter would have dispersed into nothing before the first star ignited. At the Planck epoch, the curvature parameter must have been tuned to a precision of 1 part in 10 to the 60th power. 60 decimal places of accuracy. Such a probability of arising by chance is not merely small. That probability is so close to 0 that the word unlikely fails to carry the meaning. No explanation for the balance exists within the Big Bang framework. Instead, the framework simply assumes the balance was present at the start, without accounting for why. Next came the horizon. Look at the cosmic microwave background from 2 opposite directions in the sky, the northern sky and the southern sky. In both directions, the temperature is identical, 2.725 degrees Kelvin, matching to 1 part in 100,000. But those 2 regions have never been in contact. Light, traveling at the fastest speed the universe permits, has not had enough time in 13.8 billion years to cross the distance between the 2 regions. No signal, no energy, no information of any kind has ever passed between the 2 sides. And yet both sides register the same temperature. 2 strangers who have never met, wearing identical outfits, down to the last thread. No mechanism within the standard expanding universe can synchronize the temperature of regions that have never communicated. Then came structure. Galaxies exist, and clusters of galaxies exist too. Filaments of matter stretch across hundreds of millions of light years, forming a cosmic web of extraordinary complexity. None of that structure should exist if the universe began as a perfectly uniform fog. Tiny fluctuations in the density of the early cosmos, so small that the fluctuations were invisible against the blinding glow of the plasma, had to exist in the first fraction of a second. Without those seeds, gravity would have had nothing to amplify, and the cosmos would have expanded into a featureless void. Once again, the Big Bang framework offers no source for the seeds. Once again, the framework assumes the seeds were present. Full stop. 3 problems, each an assumption baked into the foundation, each a place where the theory says this was so without explaining why. In 1981, a young physicist named Alan Guth sat in a small office, at the Stanford Linear Accelerator Center in California, staring at a notebook. Guth was not famous. At 32 years old, Guth was a postdoctoral researcher on a temporary contract, with no permanent academic position and no guarantee that a permanent position would ever arrive. Notebooks from that period survive. Tight, methodical handwriting, dense with equations that loop across page after page, and on one page, underlined twice in red ink, Guth wrote a sentence that would reshape the first fraction of a second. Spectacular realization. 2 words, written in the margin of a calculation that Guth had been running for weeks, trying to understand why the universe was so extraordinarily flat and so uniformly heated. That calculation had produced an answer so radical, Guth underlined the answer twice, because the answer required rewriting the opening moment of the cosmos. Guth called the proposal inflation. Within months of the paper reaching the physics community, the idea had traveled from Stanford to Princeton to Cambridge to Moscow, seminars filled, whiteboards covered in equations. The proposal landed with the force of a detonation in theoretical physics, because the proposal did not merely patch one problem. The proposal dissolved 3 problems simultaneously, using a single mechanism. Deceptively simple. In the first sliver of time after the Planck epoch, the universe underwent a period of exponential expansion, so violent and so rapid that the cosmos doubled in size at least 70 times in a duration shorter than the blink of an eye. Not 70 times larger, but 70 doublings, meaning 2 to the 70th power. A number so large that the expansion took a region smaller than a proton and stretched the region to a volume larger than the entire observable universe today. In that single burst, flatness was guaranteed, because any curvature present before inflation was stretched to insignificance, the way a balloon surface appears flat when the balloon is inflated to the size of a continent, and the horizon problem vanished, because regions that appear disconnected today were once a single microscopic patch in thermal equilibrium, before inflation tore the patch apart and flung the fragments to opposite ends of the sky. Seeds of structure appeared naturally too, because quantum fluctuations in the inflaton field, the hypothetical energy field driving the expansion, were stretched from subatomic scales to cosmic scales, frozen into the fabric of space as tiny density variations that gravity would spend the next 13.8 billion years amplifying into galaxies. Inflation solved all 3 problems simultaneously, elegant, testable, and in 2003, the Wilkinson microwave anisotropy probe measured the temperature fluctuations in the cosmic microwave background with enough precision to compare the pattern against inflationary predictions. Every comparison held. Angular power spectrum aligned with the inflationary prediction to a degree that no competing model could reproduce. Later, the Planck satellite, launched by the European Space Agency in 2009, refined the measurement further. A spectral index of 0.9661, plus or minus 0.0037, emerged from the data. Inflation had predicted that number. Without inflation, the standard Big Bang framework could not explain the result. But inflation did not solve the war. What inflation accomplished was explaining what happened after the Planck epoch, filling the gap between the war and the aftermath. Yet the origin, the moment the war conceals, remained untouched. Worse, inflation introduced a new mystery. What is the inflaton field? No laboratory has ever detected the particle associated with the field. No accelerator, not even the Large Hadron Collider at CERN, the most powerful machine ever built by the human species, has produced evidence that the inflaton exists. Every consequence points to an exponential expansion in the first instant, with flatness, horizon agreement, and seed fluctuations all demanding the burst. But the engine driving that expansion remains hypothetical, a ghost in the equations, absolutely necessary for the math to work, yet invisible. Invisible to every instrument that has ever been aimed at the cosmos. And the deeper question, the question inflation was never designed to answer, refuses to stay quiet. If inflation began after the Planck epoch, what started the process? What set the inflaton field to the value that triggered the expansion? And what determined the energy, the duration, the number of doublings? Every answer hides behind the same wall, the Planck epoch, the boundary where general relativity and quantum mechanics collide and neither survives. Inflation pushed the frontier of knowledge closer to the beginning, but the frontier stopped at the wall, and the wall did not move. Andrei Linde, the Russian-born physicist who extended and refined the inflationary framework throughout the 1980s, showed that inflation could begin from conditions at the Planck density, the maximum density that physics can describe before the equations break. Linde demonstrated that even in a chaotic, disordered state at that density, inflation could ignite spontaneously in random patches, each patch expanding into a separate universe with slightly different properties. Known as chaotic inflation, the proposal removed the need for special initial conditions. Inflation did not need a precisely tuned starting point. Inflation could emerge from chaos. But Linde could not remove the wall. Chaos at the Planck density still required a universe to exist, a space-time to be present, a set of physical laws to be operating. Where did the space-time come from? Where did the laws originate? Every one of those questions remains behind the wall, unanswered, perhaps unanswerable. And the community felt the weight of that limitation. At conferences throughout the 1990s and 2000s, panels on the very early universe would inevitably arrive at the same impasse. A speaker would present the latest inflationary model, the equations would work beautifully, the predictions would match the data from the microwave background, and then a hand would rise from the audience. Always the same question, phrased 100 different ways across 100 different lecture halls. What came before and what started the process? The speaker would pause. Honest ones would say directly that the question lies outside the domain of the model. Less forthcoming ones would gesture towards speculative frameworks, towards string landscapes and multiverses and eternal inflation, proposals so far beyond the reach of observation that the proposals function more as philosophy than physics. For 40 years, the same question has echoed through conference halls around the world, and the answer has never changed. Nobody knows. Erast Kleiner, a Soviet physicist, recognized the severity of the problem as early as 1965, proposing that the singularity might be replaced by a phase of exponential expansion driven by a vacuum-like state of matter. Kleiner saw, decades before Guth, that the initial singularity was not a prediction of the universe, but a failure of the model. In 1978, François Englert, Robert Brout, and Egaard Gunzig at the Free University of Brussels proposed what the group called the fireball hypothesis, an attempt to resolve the primordial singularity by replacing the infinite density with a quantum tunneling event. Alexei Starobinsky in Moscow, working independently in 1979, constructed the first semi-realistic model of an inflationary epoch using ideas from quantum gravity. Each of these physicists attacked the wall from a different angle. Each produced elegant mathematics, yet none of the proposals removed the wall. The boundary merely receded by a fraction of a second, and the mystery behind the barrier remained intact. Picture a library, a vast library containing every record of a single event: cosmic expansion, ancient glow, elemental recipe, seeds of galaxies frozen in the temperature map of the oldest light. Every record describes what happened after the first fraction of a second. The earliest record, the most ancient measurement physics can extract from the cosmos, captures a moment roughly 10 to the negative 36th seconds after whatever happened at the start. Before that moment, the library is empty. Empty. No records exist, and no measurements were ever possible, and no instruments that could be built, even in principle, that would capture information from a time closer to the origin. In extraordinary detail, the library describes the aftermath, but the event that the library was built to document, the origin itself, left no record. That event either happened before recording was possible, or was the kind of process that does not leave a trace. A name that promises an explosion, the promise of a beginning, the promise of a moment when all of existence started. But the theory delivers a description of the cooling, the expanding, the forging, the glowing, the structuring of a universe that was already underway. That beginning is not in the theory. That beginning is behind the wall, and the wall is not a gap in human knowledge that future instruments will close. Rather, the wall is a boundary in the structure of physics itself, where the rules that govern reality stop functioning, and no replacement rules have been found. Right now, as these words reach the ear, the Planck epoch, sits at the base of every cosmological model, a silent confession that the most successful scientific framework in history stops short of the one question the framework was built to answer. Expansion proves the past existed. Ancient light carries a snapshot from 380,000 years into that past. Elemental ratios carry a record from 3 minutes into that past. But the actual beginning, the moment the past began, remains behind a wall that no equation can penetrate and no instrument can see through. The most famous origin story in science does not describe the origin, and the question the wall demands, the question that has haunted cosmology since the first models predicted the singularity, is whether the origin is a mystery that physics will eventually solve, or a boundary that physics is structurally forbidden from crossing, whether the wall is temporary, a reflection of present ignorance, or permanent, a feature of the universe itself. If the wall is temporary, then human beings, given enough time and enough cleverness, will eventually understand where the cosmos came from. A permanent wall means the universe contains a secret that no intelligence, no matter how advanced, can ever extract. And that answer is not available, not because the instruments are too weak or the funding is insufficient, because the physics that would carry the answer does not yet exist and may never exist. Nobody knows, and nobody knows how to find out. For a century, the wall has stood without a single crack appearing in the barrier. Physicists who devoted entire careers to quantum gravity have published thousands of papers, trained generations of students, consumed decades of institutional funding, and produced no confirmed theory that can describe what happens at the Planck scale. The ambition has not diminished. The tools have not improved fast enough. And the evidence that the universe was once young, the evidence that points toward the wall without penetrating the barrier, is not permanent. Every pillar of the Big Bang, the expansion, the glow, the recipe, every trace the universe left behind, is subject to a force that nobody predicted and nobody can explain. A force that is slowly, quietly, irrevocably erasing the trail. That force has a name, or rather, that force has a label, because nobody knows what the force actually is. Dark energy, a term that describes a measured effect without explaining the mechanism, a placeholder attached to the most consequential discovery in the history of cosmology, and the story of how two competing teams found that force on the same night, using the same technique, arriving at the same impossible conclusion, is a story about the moment the universe stopped making sense. Start with what everyone expected. By the mid-1990s, the expansion of the universe was settled science. Hubble had measured the expansion decades earlier. The cosmic microwave background had confirmed the expansion from every direction in the sky. General relativity predicted the expansion. Every observation pointed in the same direction, and every dataset confirmed the conclusion. The universe was growing, and the fact of that growth was beyond dispute. The only remaining question, the question that consumed an entire generation of cosmologists, was whether the expansion would ever stop. Gravity should slow the expansion down. Every galaxy pulls on every other galaxy. Every atom in the cosmos tugs on every other atom. Over 13.8 billion years, that cumulative gravitational drag should be reducing the expansion rate, the same way a ball thrown upward slows as gravity pulls the ball back toward the ground. The question was not whether gravity was reducing the rate. The question was whether gravity would reduce the rate enough to halt the expansion entirely, or whether the universe would coast outward forever, gradually losing momentum, growing colder and emptier across an infinite timeline. Two outcomes. Either the universe collapses back on itself in a reverse of the Big Bang, a scenario called the Big Crunch, or the universe expands forever, thinning into an infinite cold emptiness. Both outcomes were melancholy. Both were plausible, and neither offered comfort to anyone searching for a permanent cosmos. The debate consumed entire careers. Graduate students entered cosmology programs in the 1970s and 80s specifically to answer this question. Proposals for telescope time, grant applications, doctoral theses, all framed around a single unknown. Would gravity win? Or would the expansion coast into oblivion? Distinguishing between the two required a single measurement. How fast is the expansion slowing? To answer that question, two teams set out to measure the slowdown using the brightest explosions in the cosmos. Type 1, a supernovae. These are not ordinary stellar deaths. A Type 1, a supernova occurs when a white dwarf star, the dense remnant of a sun-like star that has exhausted all fuel, gathers material from a companion star until the white dwarf exceeds a critical mass threshold. At that threshold, roughly 1.4 times the mass of the Sun, a limit named after the Indian astrophysicist Subramanian Chandrasekhar, the white dwarf detonates. The explosion is so uniform, so predictable in peak brightness, that astronomers can use each detonation as a standard candle. Measure the apparent brightness of a distant supernova. Compare the apparent brightness to the known true brightness, and the difference reveals the distance. Combine distance with redshift, and the result reveals how fast the universe was expanding at the moment the supernova exploded. Gather enough supernovae at enough distances, and a curve emerges. The shape of that curve tells you whether the expansion is slowing down, holding steady, or doing the unexpected. The Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory in California, had been hunting distant supernovae since 1988. Saul Perlmutter led the effort, and the work was extraordinarily painstaking. Distant supernovae are faint, fleeting, and rare. Catching one required scanning thousands of galaxies, comparing images taken weeks apart, and identifying the faint new point of light that signaled a detonation billions of light years away. Perlmutter had spent a decade building the pipeline, writing the software, negotiating telescope time, convincing skeptical colleagues that the measurement was even possible. In the early years, the skepticism was fierce. Senior astronomers questioned whether distant supernovae could serve as reliable standard candles at all, arguing that dust, chemical differences, and unknown evolutionary effects might sabotage the calibration. Perlmutter pushed through every objection. By 1997, the team had accumulated enough data points to begin fitting the curve. Meanwhile, a rival team had formed. The High Redshift Supernova Search Team, led by Brian Schmidt at Mount Stromlo Observatory in Australia, was pursuing the same measurement using slightly different methods. A young researcher named Adam Rees at the University of California in Berkeley handled much of the data analysis. Schmidt had assembled a group of observers and theorists scattered across 3 continents, linked by email, competing directly with Perlmutter for the same telescope time, the same supernovae, and the same answer. Both teams expected to find that gravity was winning. The question was by how much? Nobody on either team expected the answer that the data would deliver. The assumption of a slowing universe was so deeply embedded, so universally held, that the analysis pipelines were designed to measure the rate of slowdown, not to test whether the slowdown existed at all. Nobody questioned the premise. Nobody imagined the premise might be wrong. Entire careers had been built on a single assumption that gravity was winning the long war against expansion. Then, in 1998, both teams published results. And both teams found the same devastating, incomprehensible result. The expansion was not slowing. Instead, the expansion was accelerating, gaining speed with every passing moment rather than losing momentum. A mysterious pressure was pushing every galaxy away from every other galaxy, faster and faster, overcoming the gravitational drag of all the matter in the cosmos. Not coasting toward equilibrium, not breaking under the pull of gravity, actively, unmistakably accelerating. The result was so unexpected that both teams initially assumed the data contained an error. Rees spent months searching for systematic mistakes. Dust in the line of sight could dim distant supernovae, making the supernovae appear farther away than the supernovae actually were, which would mimic the signature of acceleration. Rees tested for dust. Dust could not explain the result, and neither could evolution of the supernovae themselves, a factor that might shift the calibration if the distant explosions differed from nearby ones. Rees tested every possibility, and none could account for the signal. Every systematic check came back clean. The data said the universe was accelerating, and no known error could make the signal disappear. At a conference in Marina del Rey, California, in February of 1998, Perlmutter presented the Supernova Cosmology Project results to a room of several hundred astronomers. The room fell quiet, and the silence was not the polite quiet of boredom. The silence was shock. Perlmutter showed the graph. Every data point should have curved downward, following decades of expectation. Instead, the data curved upward, showing that expansion was not slowing, but getting faster with every additional data point. Audience members exchanged glances. Several later described the moment as the most unsettling presentation they had ever attended. Astronomers who had spent decades assuming gravity would eventually halt the expansion sat in folding chairs staring at a graph that said the opposite. 2 months later, the high redshift team confirmed the finding. Two groups, using different telescopes, different software pipelines, different analysis methods, and different team members, had converged on the same impossible answer. The universe was not just expanding. The universe was expanding faster every second. Michael Turner, the cosmologist at the University of Chicago who coined the term dark energy, captured the mood in a single phrase. The most preposterous result in all of physics. Most of the total energy in the universe appeared to consist of a substance nobody could identify, a substance that exerted a repulsive pressure on the fabric of space, a force that no laboratory on Earth had ever detected. The cosmological constant, the term Einstein had added to the equations and later called a blunder, suddenly reappeared as the leading candidate explanation. Einstein had been right to add the number, wrong about the reason, and wrong to remove the constant. The universe, as always, had a sense of irony. In 2011, Perlmutter, Schmidt, and Ries shared the Nobel Prize in Physics. The award recognized one of the most important discoveries in the history of cosmology. But the prize did not resolve the mystery. Dark energy, the force driving the acceleration, remains unidentified. Roughly 68% of all the energy in the universe consists of a substance that no laboratory has ever detected, no particle accelerator has ever produced, and no theoretical framework has fully explained. The cosmological constant, the term Einstein added to the equations and later called a blunder, fits the data. But nobody knows whether the cosmological constant is the correct explanation or merely a placeholder that happens to match the observations by coincidence. The discovery earned a Nobel Prize and left behind a deeper mystery than the discovery resolved. And the implication of an accelerating expansion reaches far beyond the physics of distant supernovae. The implication reaches forward into the deep future of the cosmos. And the future the acceleration creates is one where every trace of the Big Bang eventually vanishes. Consider what acceleration means, not the concept in the abstract, the physical consequence played forward across billions of years. Right now, the night sky contains roughly 2 trillion galaxies visible to the most powerful telescopes. Each galaxy is receding from every other galaxy as space expands. Under ordinary expansion, with gravity gradually slowing the retreat, distant galaxies would remain visible indefinitely. Faint, red-shifted, but detectable. The light from those galaxies would continue arriving, stretched and dimmed but present, a permanent record of the cosmic community. Acceleration changes the outcome entirely. When the expansion accelerates, the rate at which space grows increases over time. Distant galaxies recede faster and faster. At some threshold, the recessional velocity of a galaxy exceeds the speed of light, not because the galaxy is moving through space faster than light. Relativity forbids that. Rather, the space between the observer and the galaxy is stretching so rapidly that light emitted from the galaxy can never cross the growing gap. No explosion marks the departure, and no flash signals the vanishing. The galaxy simply fades. Light stretches beyond the infrared, beyond the microwave, beyond any detector that could ever be built. Slowly, silently, the galaxy drops off the edge of the observable universe. Silently, permanently. And no signal, no measurement, no instrument of any design can recover what has been lost. One by one, the galaxies will disappear, not in a human lifetime, and not in 1,000 lifetimes either. But the process has already begun. Galaxies at the farthest edges of the observable universe are already receding faster than any signal can bridge. The boundary is creeping inward. Every passing billion years, more galaxies cross the threshold, and the observable universe shrinks. Nothing violent happens. No sound, no flash, no warning accompanies the loss. Gradually, the sky contains fewer points of light, decade by decade, eon by eon, until the sky is empty. Hold that thought for a moment, because the galaxies are not the only casualties. The evidence of the Big Bang itself, every pillar that this entire journey has examined, is subject to the same erasure. The cosmic microwave background, the ancient glow that Penzias and Wilson detected through pigeon droppings, is already stretching. Photons that carry the afterimage of the universe, at 380,000 years old, are being pulled to longer and longer wavelengths. Right now, those photons register at 2.725 degrees Kelvin, detectable by radio telescopes and microwave receivers. As the universe continues to expand, the wavelength of that ancient light will stretch further. The signal will weaken. The temperature will drop, fraction by fraction, degree by degree, below the sensitivity of any antenna that physics allows. Given enough time, the cosmic microwave background will stretch beyond the detection threshold of any conceivable instrument. The oldest light in the universe will become invisible, not destroyed, stretched to nothing. The expansion rate, the most fundamental measurement in cosmology, will also lose meaning. Hubble measured the expansion by observing the recessional velocity of galaxies, but when the galaxies have all crossed the horizon, when no external galaxy remains visible, there will be nothing left to measure the recession against. Over time, the Milky Way and a handful of galaxies, gravitationally bound in the local group, will merge into a single enormous structure. Beyond that merged supergalaxy, the sky will be empty. No galaxies receding, and no redshift to measure. Expansion itself would become invisible, as if the phenomenon had never existed. Any civilization arising in that era, looking outward with the most powerful instruments available, would see nothing beyond the stars of one merged galaxy. An island of light floating in an infinite void, with no evidence that any other galaxy ever existed, and no way to deduce that space is expanding. The elemental recipe, the prediction confirmed across 9 orders of magnitude, will survive longer than the glow or the galaxies. The hydrogen and helium ratios are encoded in the matter itself, in the composition of stars and gas clouds within the merged supergalaxy. But even those ratios will lose context. Without the cosmic microwave background to pin the baryon to photon ratio, without distant galaxies to confirm the expansion, the elemental abundances become numbers without a framework. Numbers that could mean anything. Numbers that a future civilization would have no reason to connect to a primordial forging event, because no independent evidence of a forging event would remain. Lawrence Krauss at Case Western Reserve University and Robert Scherer at Vanderbilt University in Nashville, Tennessee, explored this precise question in a remarkable analysis in 2007. The two physicists asked, if the accelerating expansion continues, what will cosmology look like in the far future? The answer was devastating. In roughly 100 billion years, every galaxy outside the local group will have crossed the cosmological horizon. The cosmic microwave background will have stretched below the threshold of any detection technology, and beyond the stars of the merged supergalaxy, the night sky will be perfectly, permanently dark, empty. Krauss and Scherer walked through the implications with methodical precision, item by item, pillar by pillar. The two physicists examined every observable feature that currently allows cosmologists to reconstruct the past, and showed that each feature will eventually vanish. Ancient glow will stretch below detectability. Expansion will become unmeasurable. Elemental abundances will persist in the matter, but without context, those numbers will be orphan data, uninterpretable. Even the cosmic neutrino background, a relic from 1 second after the beginning, currently too faint for any existing technology to detect, will be stretched into total invisibility. Any civilization arising in that era would have no evidence that the universe ever had a beginning, no expansion to measure, no ancient glow to detect, and not a single distant galaxy to observe. Scientists of that civilization, brilliant as those scientists might be, would examine the data available to them and conclude with perfect rationality and perfect confidence that the universe had always existed, a single galaxy in an infinite, static, empty void. The steady-state model, the model Fred Hoyle championed, and the cosmic microwave background destroyed, would become the only model consistent with the available observations. Not because the steady-state model is correct, not because the theory holds water, because all evidence to the contrary will have been erased. The irony cuts deeper than coincidence. Hoyle named the Big Bang as an insult on a BBC radio broadcast in 1949. The evidence proved Hoyle wrong. The cosmic microwave background destroyed the steady-state model in 1965. Hoyle fought the result for years and lost. The man who coined the name died in 2001, long after the scientific community had moved on. But given enough time, the evidence that proved Hoyle wrong will disappear, and the observable universe will look exactly the way Hoyle said the universe should look: an eternal cosmos with no birthday. Not because Hoyle was right, because the expansion that proved the universe had a past will eventually erase the proof. The greatest vindication and the greatest erasure linked by the same force. And the lithium crack, the stubborn factor of 3 that haunted the recipe for 4 decades, will become irrelevant, not resolved, not explained, simply forgotten, along with every equation and every framework that produced the prediction. The crack, the triumphs, the accidental discovery through pigeon droppings, the wrong number that humiliated the field for 23 years, the man who gave the theory a name born from contempt, all of the evidence, all of the history, all of the human drama that surrounded the most successful scientific framework in history will be gone. Not because someone destroyed the records, because the universe itself will have stretched the records beyond recovery. Now step back and look at the whole picture, because the full weight of what is happening, the scope and the permanence of the erasure, deserves a moment of stillness. Right now, as these words reach the ear, the evidence exists. The cosmic microwave background is passing through the walls of every building on Earth, through the bodies of every person alive, through the same instruments that detected the signal more than 60 years ago. That ancient light has been traveling for 13.8 billion years, carrying the afterimage of a moment when the universe was young and hot and opaque, real and measurable, and here, the galaxies are still visible, 2 trillion of them scattered across the observable universe, each one receding, each one carrying a redshift that encodes the history of the expansion. The recipe is still legible. Hydrogen, helium, deuterium, measured in the atmospheres of the oldest stars in the most pristine gas clouds, preserving the record of the first 20 minutes. The lithium crack is still open, still unexplained, still demanding an answer that has not arrived. Every pillar of the Big Bang framework, every piece of evidence that the universe was once unimaginably young and unimaginably hot, exists right now, available, detectable, and fully open to study. And every single pillar is temporary. The expansion that delivered the evidence is the same expansion that will erase the evidence. Builder and destroyer, the same force, separated only by time. A name that was a lie, coined by a man who wanted the idea to die. A first measurement wrong by a factor of 7, humiliating the framework for 2 decades. Proof that arrived by accident through engineers who did not understand what the engineers had found, while the trained cosmologists arrived too late. A recipe that matched 3 elements perfectly and failed for a 4th. A crack resisting every proposed repair for more than 40 years. A beginning hidden behind a wall that no equation can penetrate and no instrument can see through. And the evidence itself, every pillar, every trace, every breadcrumb, the universe left behind is being erased by a force nobody can identify at a rate nobody can stop, toward a future nobody can prevent. And the question Krauss and Scherer raised carries one final sting. Those future scientists will not know they are missing anything. What makes the erasure so devastating is that the absence of evidence will not feel like a gap. The absence will feel like completeness. A single galaxy in an infinite void is a perfectly consistent cosmological picture, clean, elegant, and completely wrong, but indistinguishable from correct when the data that would reveal the error no longer exists. The universe did not owe anyone evidence. Nothing in the laws of physics guarantees that evidence of a beginning will survive long enough for anyone to find the traces. Ancient glow could have dispersed before any intelligence arose to detect the signal. Elemental ratios could have been overwritten by stellar processing before anyone measured the numbers. Expansion could have slowed so gradually that no civilization would have noticed the expansion for millions of years. None of that evidence had to survive, none had to be detectable, and none had to arrive at a moment in cosmic history when a species existed with the technology and the curiosity to interpret what the evidence meant. But the evidence is here, right now. In this sliver of cosmic time between the moment the universe cooled enough for light to travel and the moment the expansion stretches that light beyond detection, the trail is visible. Breadcrumbs glow in the ancient light. Every recipe remains legible, and the crack is still open, still unexplained, and the wall stands silent and immovable, guarding whatever happened at the start. To be alive in a sliver of cosmic time while the trail still exists, while the breadcrumbs still glow, is not ordinary. The window is open now, but the window will not remain open forever. Not because of any catastrophe or any failure of human effort. Because the same expansion that proved the universe had a past will eventually erase the proof. The universe is telling a story about where all matter and all energy and all space originated. And the universe is also, slowly and irrevocably, taking the story back. The ancient glow fills all of space, fading so slowly that no human lifetime will notice the change. But the glow is fading, and one day the last photon of that ancient light will stretch beyond detection. The sky will forget that the sky ever remembered, and the universe will continue, vast and silent, carrying a secret that nobody will ever know was there. The name was an insult. Fred Hoyle sneered 3 words into a BBC microphone, expecting the ridicule to bury the idea forever. The ridicule became the brand, and the brand turned out to be more honest than Hoyle ever intended, because the name carried the same absurd energy as the truth. The measurement was wrong by a factor of 7. Proof arrived through pigeon droppings delivered by engineers who had no idea what the antenna had captured. A recipe matched 3 elements with breathtaking precision and failed for a 4th. The beginning hides behind a wall where every known equation stops functioning, and the evidence, every breadcrumb the universe left behind, is being stretched into silence by a force nobody can name. Each certainty fell. Each fall revealed a deeper layer. Every deeper layer pointed toward a moment that no instrument can reach. But the universe did not owe anyone a trail. No principle demanded that the afterglow persist long enough for anyone to notice. Heat from that ancient epoch could have faded below detection before any mind built the instruments to measure the temperature. Chemical fingerprints from those first 20 minutes could have been consumed by stellar furnaces long before any observer decoded the ratios. No trace was required. None was guaranteed. The Big Bang is not the story of how the universe began. The Big Bang is the story of what the universe did next, and the fact that the universe left behind any record at all, a glow, a recipe, a rush of galaxies pulling apart, deserves the most wonder. A trail written in light and elements and the shape of space, evidence of a process that occurred before evidence was possible. To be alive while the trail still glows is not ordinary. That window will close, not because of any catastrophe and not because of any failure, but because the very mechanism that revealed the past is also dismantling every record of that past. One by one, galaxies are slipping beyond the horizon where no signal can follow, and the ancient light is stretching towards silence. But today, the glow is here, passing through the walls around you, faint and ancient and everywhere, still carrying the memory of a moment 13 billion years in the past. The sky remembers. For now, what we have just uncovered is not just a fact about the Big Bang. The discovery is evidence that our intuitions about the beginning of the universe are completely wrong. A recipe that works for 3 elements breaks for a 4th. The beginning hides behind a wall no equation can cross. And that gap between what we thought and what is actually true That is where science thrives. If you want to help me improve the quality of this channel and tackle even bigger topics, hitting that like and subscribe goes a long way. Your support keeps that process alive and lets me go deeper on the subjects that matter most. But mostly, I want to know what you think. Did I miss anything about the Big Bang and the evidence behind the theory? Let me know in the comments. I will catch you in the next one. Let curiosity guide you, keep learning, and know that you are always appreciated.